Now friends, we shall discuss the AC circuits that we have discussed in a classical way by J operator method. This is a wonderful technique and it makes the discussion very simple. The thing that we have discussed for fairly few minutes will be quickly sorted using J operator. Now imagine a circle of radius 4. So every point on the circle is at distance 4 units from origin, and we have uh, the intersection of the circle with x and y axis. X axis I reserve for real and the y axis for imaginary. Now the coordinates of A, B, C, D points will be 4, 0, 0, 4, minus 4, 0 and 0, minus 4. Now uh, we have A, which is an ordered pair in complex numbers, 4, 0 equal to 4 plus j times 0. Here this j is under root minus 1, the way we represent complex number I, but the notation is reserved as j operator, so this time j equal to under root minus 1. Now the point B, which has coordinates 0, 4, we have B equal to J operator operated on A. A we have written as 4 plus J times 0. So J is again operated on 4 plus J times 0. It will be now J times 4 and 0. So the real coordinate is 0 and imaginary coordinate is 4. So 90-degree rotation we have uh, devised using operation of J on the point A. Now the third point C minus 4, 0. The point C minus 4, 0 can be represented by twice operation of J operator, which we write J square on point A. Point A is 4 plus J times 0. J square is minus 1, so minus 4 plus 0. So minus 4 plus J times 0. This point can be obtained by again rotating the point B through 90-degree, and that 90-degree rotation is corresponding to one operation of J operator on the point. Similarly, the fourth point in the discussion D can be obtained by 3 times rotation through 90-degree. So 3 J operators, which we can write J cube, and J cube is obviously minus J. J square is minus 1, minus 1 multiplied by J will be J cube. Now the basic point is 4 plus J times 0. So minus J operated on it will yield 0 minus J times 4. So here the ordered pair you can say 0 minus 4. Now one more rotation through 90-degree will be J to the power 4, and J square is minus 1 and square of that will be plus 1, and it is 4 plus J times 0. So we are back to the original point after 360-degree rotation. Now we have x plus jy, the point in the Argand plane, in polar form. Euler's identity, we have r into e to the power j phi. So if r is 1, we can write cos of phi plus j times sine of phi. Now here we have the first point 0 plus j times 1, that we can write simply as j, and it can be written as r into e to the power j times phi by 2. So here you can consider r to be 1, and we can write j by e to the power j pi by 2. J square you can write e to the power j times pi. J cube you can write e to the power j times 3 pi by 2, and so on. Now, in terms of this Euler's identity, e to the power j theta is cos theta plus j times sin theta, and another identity, e to the power minus j theta is equal to cos theta minus j times sin theta. So here we have 4 points. Now we shall represent this in terms of Euler's identity. So A can be represented by 4, that is r, into e to the power j phi. R is called modulus, and this 0 appearing with j or theta you can call modulus. 4 cos of 0 plus j times sine of 0. Cos of 0 is 1, sine of 0 is 0. So here we have this number 40 represented using this polar representation. Similarly, the next point can be represented by 4 e to the power j pi by 2 and cos of pi by 2 plus j times sine of pi by 2. Cos of pi by 2 is 0, sine of pi by 2 is 1, and we have this ordered pair 0, 4. 0 plus j times 1 whole thing multiplied by 4. So in this fashion we can have rotation through pi encompassed into the j operator representation of exponential function, and here 273-degree rotation 3 pi by 2 and one complete rotation. So here 90-degree rotation can be represented by j, 180-degree rotation can be represented by j square, and so on. So here as omega rolls, so this rotation is being represented by j operator. Another example, I would recommend students to pause this video at this point and can understand the figures for 5. I mean R5 and phi rolling over 0 to 2 pi. Now in the Argand plane we have a point P xy or z equal to x plus iy. It can be represented as r plus j times x. R is the real part, x is a kind of reactance, capacitive or inductive, that depends. Now this side on x-axis or real axis is r cos theta, r cos phi, and this side is r sin theta or r sin phi. So the magnitude, which is modulus of z equal to r, it can be under root of capital R square plus capital X square, and theta is equal to tan inverse of x upon r, that is imaginary part upon a real part. Now the signals which are sinusoidal or cosinusoidal can be represented by this Euler's identity, and V of t is equal to V0 e to the power j omega t equal to V0 cos omega t plus j times sin omega t. If you like sine representation, you can pick up imaginary part and compare the equations. If you like cosinusoidal function, you can pick up a real part of this. Current can be represented similarly as I0 e to the power j omega t. Now we are equipped with the j operator to represent the things, and now V of t, that is instantaneous voltage, can be represented by V0 e to the power j omega t. The drop across resistance will be IR, and we can write IR equal to V0 e to the power j omega t, and you can simplify I of t equal to I0 e to the power j omega t, where I0 is V0 upon R. So we have both the things in pure resistive circuit in phase we have already discussed. Now for pure inductive circuit we have VL equal to L times di by dt. Now applying Kirchhoff's voltage law, VL is equal to V of t L into di by dt equal to V0 e to the power j omega t. Separating variables and performing integration will solve this differential equation. And now here we have a little different additional information. Integration di of t will be I of t equal to V0 upon L. Integration e to the power j omega t will be same integration e to the power j omega t divided by j omega. So here quantity j is appearing in addition to omega L in the denominator. So this quantity can be represented as complex impedance. So we reserve a letter capital Z for complex impedance, and if we want to represent only omega L associated with that, we have reserved letter that capital X, which represent inductive reactance. So reactance multiplied by J will be impedance. Now this J can be represented by e to the power j pi by 2. So we are trying to represent some quantity on imaginary axis, so which is flipped by pi by 2 angle in reference to x-axis, and I0 is equal to V0 upon omega L, that is V0 upon XL, that is usual quantity that we were having, XL equal to omega L. And if we like to represent j omega L as ZL, that also we can do. So here we have I of t equal to V0 upon XL. Now e to the power j omega t minus pi by 2. So here in the red square, red rectangle, we have current and voltage, and here you can see in pure inductive circuit the current lags by pi by 2. We have already discussed what the word lag means in terms of phase. In pure capacitive circuit, we again have V of t equal to V0 e to the power j omega t. Voltage across capacitor is Q of t upon C, and Q of t upon C by KVL is equal to V0 e to the power j omega t. If we take C on right hand side and differentiate this equation with respect to time, we'll be able to obtain current, and that is our objective. So current in the circuit is d dt of Q of t, that is equal to j omega times e to the power j omega t. So V0 multiplied by j omega c will be the part pre-exponential factor, and e to the power j omega t as it is. Now we want to enforce V0 upon something, so we have 1 upon j omega c to represent that, and 1 upon j omega c is the complex impedance offered by capacitor. This is a new definition for us, and if we represent this j by e to the power j pi by 2, which is cos of pi by 2 plus j times sine of pi by 2, and this e to the power j pi by 2 will appear here. See, this j is here, so this angle is positive, and I of t equal to V0 upon xc into e to the power j omega t plus pi by 2. So here in the red rectangle we have the final equation for current, and it indicates it is ahead by pi by 2. The capacitive reactance is 1 by omega c, and the complex quantity, that is complex impedance offered by pure capacitor is 1 upon j omega c. Few authors may write this as minus j in the numerator divided by omega c, is one and the same thing. Now we can quickly go through the AC circuit using J operator. The obvious Kirchhoff's voltage law is VR plus VL plus VC equal to V of t, and VR is equal to I into R, VL is L di by dt, and VC is Q by C. So if we couple together all these terms and we propose that the solution, naturally we'll have a form I0 e to the power j omega t minus phi, where we consider that phi is to be found and I0 is to be found. To do so, we shall complete this equation, first differential equation, in terms of this solution. To do so, we need to differentiate I of t with respect to time. So j omega times I0 e to the power j omega t minus phi will be the time derivative, and to find the instantaneous charge in the circuit, we need to integrate this equation, and by the operation of integration, we have j omega in the denominator, and we can substitute all these values and we get this final equation. So here colorful underline indicates respective substitution, and by substituting that you can rearrange the equation. I again recommend the beginners to pick up a piece of paper and try this equation on their own, and you can see that I0 is equal to V0 upon R plus J is taken common, omega L minus 1 upon omega C. So here the term in the denominator is a complex number, real part plus imaginary part. You can consider ordered pair, or you can think it as x plus jy, and the total complex impedance by LCR circuit can be represented by this capital Z, and Z is equal to R plus J times omega L minus 1 upon omega C. Now this Z x plus jy can be represented as R into e to the power j phi. Here I missed typing j, but you consider that this is j phi, and R is equal to under root x square plus y square, and phi is equal to tan inverse of y by x. So here in R terms, this R is equal to under root of R square, capital R square, plus omega L minus 1 upon omega C whole square, and phi is tan inverse of omega L minus 1 upon omega C upon R. That's it. Here, if you like to represent the pure reactance term for the total LCR series combination, you may write this x as under root of this quantity. Now, this x will be minimum when omega L is equal to omega C, and under that condition that minimum value will be R. So the resonance frequency omega R is 1 upon under root of LC, and x minimum here will be capital R. There won't be any phase difference under this situation, because omega L minus 1 upon omega C is 0, and tan inverse of 0 is 0. So we have completed this discussion. Now Q factor. This capital X reactance we have written like this, and omega at resonance is omega R upon R, and again in the second term 1 upon omega, so this omega is replaced by omega R into capital R. So this offers us quality factor omega R L upon R, In another term, it can be written as 1 upon omega r into capital R into C. Now this graph shows that at the particular resonance frequency, the reactance offered is minimum, and as the reactance is minimum, the RMS value of current will be maximum. So here you can see the maxima to the contour, and the sharpness of maxima goes on increasing, which is determined by the quality factor, and the quality factor is represented like this. For different values of L, C, R and RMS value, this graph is plotted to the scale. This is again a series combination that we have started, and omega resonance frequency will be 1 upon under root LC. It doesn't depend upon the value of resistance. It depends upon value of inductor and capacitance. Now we shall quickly go through the parallel circuit. We have resistance and inductor in series, and the whole stuff is shunted by a capacitor. Now IL will be instantaneous voltage divided by the reactance of series combination of L and R. So R is pure, omega L is lagging by pi by 2, represented by this J. Now R plus J omega L will be the reactance, complex impedance of series combination of L and R, and the complex impedance by capacitor will be J omega C, 1 over J omega C. Now here we shall consider currents, and total current will be sum of the part going through inductor and capacitor. So instead of Kirchhoff's voltage law, we shall have Kirchhoff's current law. Voltage is being represented by V0 e to the power j omega t. Now here we can plug in the values V of t divided by Z. So for pure capacitive part, the second term will appear, and series combination of inductor and resistor is represented here, and 1 by Z is equal to 1 upon R plus J omega L plus J omega C. Now we have to simplify this. LCM we shall consider R plus J omega L, and by considering R plus J omega L LCM, we are having 1 plus J omega C multiplied by this LCM. So you can simplify and sort out real part and imaginary part. After doing that, after that simplification, 1 minus omega square LC is the real part and omega CR is the imaginary part, divided by R plus J omega L. Now to make denominator real, we shall multiply by complex conjugate. To leave our equation unaffected, we have complex conjugate of the denominator term multiplied and divided, so that in the denominator we have R square plus omega square L square, and here you have to again pick up a piece of paper and pencil and simplify, and you can pause the video, and by that calculation you will appreciate that on the numerator we have R plus J omega times CR square minus L inside bracket 1 minus omega square LC. Now, so friends, again we have the sorted out term 1 upon Z equal to so and so, and 1 upon Z you can call 1 upon complex impedance you can call admittance, complex admittance, and it looks like this. And if you take modulus of that. So you have real part square plus imaginary part square in the under root divided by this real number r square plus omega square L square. And the minimum value of this under root will be r when cr square is equal to L times 1 minus omega square LC. For that minimum value, we have Cr square equal to L times 1 minus omega square Lc. You can simplify this and it turns out that omega is equal to under root of 1 by Lc minus R square upon L square. If you pick up the resistive part 0, then omega will be under root of 1 by Lc. So it looks similar to that of the series resonance circuit. And the quality factor will determine how sharp your impedance with frequency appears. So here you have maximum impedance as a function of frequency, and on either side of this the impedance goes on decreasing. For maximum impedance which appears in the denominator, if you plot in terms of current, the current will be minimum for maximum impedance. This is how we complete the discussion of the LCR circuit.